Dear students, now we are going to discuss about Boolean algebra, its laws, properties and applications. Charles Boole in 1854 introduced the concept called Boolean algebra. It is an algebraic structure defined by a set of elements with two binary operations that are Boolean sum and Boolean product and one unary operation that is called as complement operation. Here we are talking about set of elements. Set of elements here are binary 1 or 0. Binary 1 represents high value. Binary 0 represents low value. Okay. So it is a set of rules mainly used to simplify the logical expressions. So logic means here it is used in digital circuits. Boolean sum can be expressed like that: 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 0 is equal to 1, 1 plus 1 is equal to 1. In case of binary addition, 1 plus 1 is equal to 1, 0. Correct? But in this Boolean sum, 1 plus 1 is equal to 1. Boolean product can be written like this: 0 into 0 is equal to 0, 0 dot 1 is equal to 0, 1 dot 0 is equal to 0, 1 dot 1 is equal to 1. Boolean algebra is mainly used to analyze and simplify the digital logic circuits. Here digital logic circuits are like OR gates, AND gate, NOT gates. Okay, these are the digital logic circuits. Next we are going to discuss about fundamental laws of Boolean algebra. First one is annulment. Here we represent the element as A. In Boolean algebra, we are going to use only the binary values. It can be either 0 or 1. So in this one, A plus 1 is equal to 1. That means anything plus 1 is equal to 1. Suppose A is equal to 0. 0 plus 1 is equal to 1. A is equal to 1. 1 plus 1 is equal to 1. Correct? So here in this product expression, A multiplied with 0 is equal to 0. As we know that any values multiplied with 0 is always 0. If A is equal to 1, 1 is multiplied with 0 is equal to 0. If A is equal to 0, 0 into 0 is also 0. So these are the very important expressions. Here identity. A plus 0 is equal to A. If A is equal to 1, 1 plus 0 is equal to 1. A is equal to 0. 0 plus 0 is equal to 0. So any value added with the 0 is equal to the same value. Here in multiplication, any values of A multiplied with 1 is the same value as such. For example, if A is equal to 1, 1 dot 1 is equal to 1. A is equal to 0 means 0 dot 1 is equal to 0. Okay. So these two are the identity laws. So next complement. In this complement, if A is equal to 0, then A complement is equal to 1. Using this complement property, we can obtain two expressions, that is A plus A bar is equal to 1. If A is equal to 0, so what is the value of A bar? It is 1. So 0 plus 1 is equal to 1. If A is equal to 1, A bar value is 0. Correct? It is the complement. Obviously it is equal to 0. If we are going to add any value with its complement, it is always 1. So next, if any value is multiplied with its complement, the resultant value is always 0. The same concept. If A is equal to 1, then a bar is equal to 0. 1 into 0 is equal to 0. So next one is double negation. So in this one, we know that is equal to 0 means a bar is equal to 1. If I am going to take one more complement for this complemented value, I can get the answer as 1 bar is equal to 0. It is equal to a. Okay. So next one is idempotent class. So in this idempotent class, the first expression is a plus a is equal to a. The second expression is a dot a is equal to a itself. So now we are going to prove these two laws. So in this first one, the proof, we are going to take this left hand side. This a plus a, this value is multiplied with a plus a minus a bar. Here a plus a bar is always 1, correct? So here we can use this value. So in this left hand side we can take a plus a, that is multiplied with 1. There is no change. This 1 can be written as a plus a bar. So in the next step, we have to multiply the terms inside with this bracket. We can obtain a into a plus a into a bar. A into a bar. So next, a into a. We can get a into a plus a into a bar. As we know that a into a bar is always 0. A into a bar is always 0. So this a into a is equal to a plus this a into a is equal to a. We can take this a as a common, then what is the remaining term? 1 plus 1. So 1 plus 1, that Boolean sum is equal to 1. So the answer is equal to a. So we can get the right hand side as a. We have proved the first expression, a plus a is equal to a itself. So come to the second expression. So in this second expression, we are going to take the left hand side. So a dot a plus 0. Correct. So anything plus 0, it is equal to the same value. So here we can write a dot a plus 0 can be written as a into a bar. Correct. A into a bar is always 0. So here we can take this a as a common term. So here a into the remaining term is a plus a bar. A plus a bar is always equal to 1. So 1 into a, that answer is a. So a multiplied with the same value a results the same value as a. Okay. A dot a is equal to a. So next one is absorption loss. In this absorption loss, the first expression is a plus ab is equal to a. Here we can take the left hand side a plus ab. Correct. So here a is a common term. We can take it outside. So we can get 1 plus b. Correct. So 1 plus b. 1 plus any values. Any value. Okay. So that is equal to 1 itself. So here this becomes 1. So a into 1 is equal to a. So it is proved. So consider the second expression a into a plus b is equal to a. Here we are going to take this left hand side a into a plus b. Multiply inside, we can get a into a plus a into b. A into a is always a. Correct. So a into a is equal to a. We can write a plus this ab. As we have already derived, a plus ab is equal to what? A. The same steps we have to follow. We can take a outside. So 1 plus b. 1 plus any value is equal to 1 always. So here 1 into a is equal to a. Okay. So these two are the absorption laws. The next expression is a plus a bar b is equal to a plus b. Here we have to take this left hand side for proof a plus a bar b. For further simplification, we have to multiply this a with 1 plus b. 1 plus any value is equal to 1 always. So a is multiplied with 1. That 1 can be written as 1 plus b. And here this value is a bar b. Next we can multiply inside this. We can get a plus ab plus a bar b. Correct. So here in this case, we can take this b outside. We can obtain a plus b of a plus a bar. A plus a bar. So any value added with its complicate is always equal to 1. So here we can obtain a plus b. This b is multiplied with 1. So it is only b. We have obtained the right hand side now. Correct. So we have proved this law. The next expression is a into a bar plus b is equal to ab. So it is very simple. We can multiply inside this. So we can get a bar plus a into b. A bar is always 0. Any value multiplied with its complicate is always 0. So 0 plus AB, the answer is AB itself. Okay. So we have proved the given law. These all are the fundamental laws of Boolean algebra. By using these laws, we can easily analyze and simplify any complicated digital logic circuits. So next one is properties of Boolean algebra. Boolean algebra can satisfy three properties: commutative property, associative property and distributive property. In commutative property, the sequence can be changed in any order. That means changing the sequence does not affect the output of the logic circuit. A plus B is equal to B plus A. The same can be applicable for product. A dot B is equal to B dot A. Associative property. In associative property, we can use more than two variables. So, A plus B plus C, that is equal to A plus B plus C. The same can be applicable for product. A dot B dot C, that is equal to A dot B and then dot C. So, next one is distributive property. Here, we can have product along with addition. So, A dot B plus C, that is equal to A dot B plus A dot C. The same in the reverse order, A plus B dot C can be written as A plus B dot A plus C. These are the properties of Boolean algebra. Applications of Boolean algebra. Boolean algebra is used in the theory of probability and information theory. As we know that Boolean algebra is a part of mathematical analysis, especially used in digital circuits. So it is widely used in digital computers to solve the logic expressions in digital systems in an easy way. It is also used in set theory and statistics.